Okay, so now we're taking a look at question 2 from the 2010 scholarship paper. And we're just going to do a separate video for part A because there's quite a bit to part B, so we'll do that as a separate video. The second ionization energy is the energy required for the complete removal of 1 mole of electrons from 1 mole of gaseous ions. And you're given a general equation for that, so you need to be aware that it's already ionized, and then it takes more energy to remove the second electron, typically, than to remove that first one. And this is per mole of the species which is in its gaseous state. The graph shows the second ionization energy for the elements of period 4. So starting with potassium in group 1 and finishing with krypton in group 8 or group 18. So that's across an entire period. The general trend should be that ionization energy should increase from left to right as you go across the periodic table. And this is because you're increasing the atomic number and therefore the effective nuclear charge, or ZF, which is the ability of the nucleus to attract those outermost shell or valence shell electrons towards it. It also matches up that electronegativity of elements increases as you go across the periodic table as well because of that increase in atomic number. And the question they're asking here is to discuss the trend in second ionization energy for the elements of period 4 and to account for deviations or anomalies from the trend in terms of electron configuration. So what I've done is in pink, I've drawn a line and a little tick here to show elements which follow the trend. So for example, from calcium to vanadium there, you can see there's an increase in ionization energy, which is what you'd expect. Then we have an anomaly here, which I've marked as number 2, as you go from chromium to magnesium. So we discussed those two elements right there. Then the trend continues as normal, and then there's an anomaly again between copper and gallium. So we'll discuss that anomaly as anomaly number 3. And then the trend starts to continue again. There's a drop there. We could discuss that between gallium and germanium. We could discuss that as well, actually. And then the trend increases. Then there's not much of a difference between these two elements. And then there's a big jump up here to krypton at the end. So these trends are discussed in detail in the answers from the NCA guys. They're discussed quite well, but I'll go through them individually just to explain each one. The first one being, why is there such a dramatic drop from when you move from potassium to calcium from group 1 to group 2? And the other thing you can add to your periodic table just to help, because this is all about moving between orbitals, is that you can add the type of orbitals that these elements belong to. So group 1 and group 2, they're going to be s orbitals, so the s block, also referred to as the s block. And then from scandium all the way to zinc, so from scandium all the way to zinc, these are going to be d block electrons, or d block elements. And then for the rest of these, the other 6 here, we have the 1, 2, 3, 4, 5, 6, we have the p block. And that tells you what orbital the electrons should typically be in, and that helps you discuss some of these anomalies. Okay, so what I'm going to do is I'm going to discuss each one of these numbered anomalies on the next page in as succinct detail as possible. Okay, so the key to addressing all these anomalies, well, first of all, have the graph in front of you as you watch this video, because otherwise a lot of this won't make sense. But the key to explaining these anomalies is to just write down the correct electron configuration for the two ions in question. So we're starting, in all cases, we're starting with the first ionic state, the +1 state. And then for potassium plus, what you have is the electron configuration is everything as far as neon, then it's 3s2, 3p6. And it's that situation versus for calcium plus ion, which is everything as far as argon, and then 4s1. So hopefully it's evident now that you can see that to ionize, further ionize calcium positive, you need to remove an electron. First of all, you're removing 1 electron from an already full p orbital. 6 electrons means it's full, which is also in an energy level closer to the nucleus. So energy level 3 is closer than energy level 4, which is calcium plus, is the state that calcium plus is in. And also this is only half filled, and it's a smaller orbital. So it's half filled, smaller orbital, further from the nucleus, and therefore it's much easier to remove this electron than it is to remove one from those right there. And that accounts for that big drop on your graph. That accounts for that right there. So we've done that much. The next anomaly we want to take a look at is the one when you compare chromium and manganese. So the trend drops, and why is that? So let's take a look at the second one. So the second situation we're going to look at here is from chromium plus to manganese. And there's a slight drop, and we want to explain this anomaly. Why is there that slight drop? So again, electron configurations, you need to do them correctly, otherwise you won't get the right explanation. So I found the best starting place for chromium to work at chromium plus's electron configuration was to start with the initial electron configuration of chromium element, so elemental chromium. So chromium is going to be everything as far as argon, and then it's going to be 3d4 4s2. But what, of course, chromium is one of the two exceptions that you learn in level 3 when you're doing your electron configurations. And actually, to stabilize that d orbital, chromium's actual electron configuration is 3d5 4s2 4s1, 3d5 4s1. So that's one of the d block exceptions. And so you need to remember that. So that's your starting point. And then to ionize that, so to ionize this, you need to remember that you remove the electron from the highest energy orbital, which in this case is the 4s orbital. So what you get here is after you ionize chromium, you get chromium plus, which is everything as far as argon, and then it's going to be 3d5, and you've removed this electron right here. So that's the situation. So you're comparing a situation where you have a half-filled d orbital, which is quite stable, relatively stable, and you're comparing that to the situation for manganese. Manganese would have originally been, for manganese elemental, it would have been everything as far as argon, 3d5 4s2, and then when you ionize manganese, you get everything as far as argon, 3d5 4s1. So the situation here is that you're trying to remove an electron which is further from the nucleus, and it's in a smaller orbital. S orbital smaller than a p, and it's only half filled, which is not, well, a half filled s orbital is not as stable as a half filled 3d orbital, but the main difference is that it's in an energy level which is further from the nucleus, therefore easier to remove that electron. So that should account for that drop in energy right there. So we've done number 1 and number 2. Number 3, there's anomaly here between nickel, copper, zinc, and gallium. So these 3 elements right here. So let's discuss that anomaly. So again, to discuss the anomaly between these 3 ionic states, we're just going to write down the correct electron configurations. So copper, elemental copper would have started off as everything as far as argon, 3d10 and then 4s1. And again, the d orbital is filled before the s orbital in this case because of extra stability of that full d orbital. And then copper ion then is going to be everything as far as argon, 3d10, and then the 4s orbital is emptied completely in that case. So straight away you can see this is very stable situation. You have your full 3d orbital there, therefore the ionization energy for your copper is greater than the ionization energy for your zinc situation. And why is that? So let's take a look at zinc then. Zinc is going to be zinc positive ion now is going to be everything as far as argon, 3d10 4s1. So what you're doing here, same situation as we had for the other two anomalies. To remove an electron from a energy level 4 is easier. Energy level 4 is easier than from level 3 because it's further from the nucleus. And you have an s orbital as well, which is smaller, but the main point here is further from the nucleus, and it's only half filled as well versus something which is fully filled. So that's why there's a slight drop right here. So there's a drop as you go from copper to zinc, and then there's an increase again as you go to gallium. So let's just put gallium beside those two. Gallium's ion Ga positive is going to be everything as far as argon. It's going to be 3d10 4s2, and then the p orbital in this case has been emptied, so the 4p orbital has been emptied, and so then you have 3d10 4s2, which accounts for the increase again because it's two full orbitals, which of course are very stable, so therefore it takes more energy than the zinc plus situation, this situation versus that situation. You can see that on your graph. The energy starts to increase again as we go from zinc to gallium. Okay, and there's further anomalies there. There's a drop as you go from gallium to germanium, and we'll just use the NCA explanations for this. And there's also an increase there as you go from bromium to krypton, but this is going to be its octet to be used to explain that. But let's take a look at the answers just for the remainder. So we've done everything here. We've done all of these. And just for the remainder, so we've done, okay, gallium we didn't, or germanium we didn't do. Germanium has the electron configuration, everything as far as argon, 4s2, 4p2. It needs less energy than gallium, because gallium there, if we just write it, was everything as far as argon, 3d10, 4s2. And so they're doing this as the electron configuration for elemental germanium, but germanium, which has lost an electron, will be 4p1. So this needs less energy than gallium, as the second electron comes from 4p right there, which is further from the nucleus than the 4s electrons right there removed from gallium. So that's why the energy drops slightly well, that's why less energy. Yeah, so I had to just double check the graph there. So that is why germanium needs less energy than gallium to remove that second electron, because germanium, you're taking it from a 4p orbital, you only need to remove one electron, versus the gallium situation where you're trying to take it from a filled 4s orbital. 4p is actually further from the nucleus as well, because 4s is right here. So further from the nucleus and not a full orbital. And that accounts for this anomaly right here, from gallium to germanium. Then the trend behaves as normal. And then there's one final thing to point out, which is the similarity in ionization energy for scandium and bromine rather. And that's just explained here as well by the NCE answer. So bromine has the electron configuration 3d10, 4s2, 4p5. Needs less energy than expected, as the electron removed is the last paired electron in 4p5. So if we represent the p orbital like this, we have the subshells, and you fill each subshell individually first of all, and then you pair them up. So this would be a situation for 4p, so 4p5 would be right there. Needs less energy than expected, as the electron removed is the last paired electron in 4p5. Okay, so again, I'm confusing you here because this is the elemental stage. The ion is going to be 4p4, and so that situation is going to be like that. And your 4 electrons are going to be arranged like that. So to remove this 1 electron here will actually be more energetically favorable, because you'll end up with a half-filled p orbital, which will just have 3 electrons in it like that. which is more stable, and that's why it takes a surprisingly less energy to ionize B or positive. So there is your comprehensive answer for question 2 part A. And question 2 part B, we'll do a separate video for that to explain that one.